this is Tim Hsu again from San Jose State University, and I'm here today to talk about some basic derivative formulas. I'll start with the derivatives of power and exponential functions. I'll go through some straightforward algebraic rules for derivatives, and then I'll talk about some examples. What can we now compute using these rules? And also, maybe just as importantly, some non-examples. What can we not yet compute using only the rules that we know so far? Okay, so previously on Calculus 1, I hope that at this point you've seen that given a function f, the derivative of f is defined to be f prime of x is the limit as h approaches 0 of f of x plus h minus f of x all over h. So you take this stuff and then you calculate its limit as h approaches 0, and the x will still be left over, and so this is now a function of x. Anyway, oh yeah, so that's true. So that's what f prime of x is for each value of x for which this limit exists. So in this video, I'm going to talk about how to compute f prime of x for some examples of f of x with relatively uncomplicated formulas, some relatively straightforward things. Okay, to start off, here's some examples that have constant derivatives. So remember, a constant function has a horizontal straight line, so that always has slope 0, and so that for any constant c, the derivative of c is equal to 0. Okay, similarly, since the line y equals x goes like whoop, has constant slope 1, we see that the derivative of the function x with respect to x is equal to 1. All right, more generally, we can show that, well, you can prove it, but if you want to see the details, it's in whatever book you're using, but what you really need to know is that just the fact that the derivative of x to the n is equal to n times x to the n minus 1. And what's a good way to remember that? So if you want to take the derivative of a power function, x to the n, what you do is you move the exponent out front, so the n sort of comes down out front, and then subtract 1 from the exponent. So there was an n up here. I pulled it down up front and then subtracted 1 from it. So notice that when n is equal to 1, if you apply the same rule, then the 1 comes out front and the 1 becomes 0 up here, and x to the 0 is just 1. And so, the fact that the derivative of the function x is equal to 1 is simply the case n equals 1 of this rule. All right, now exponential functions. So remember how probably if you saw the video that I made of this, and probably your instructor said the same thing, that the real definition of e is that e to the x is the awesomest exponential function. Awesomest exponential function with the awesomest calculus properties. Well, here's exactly what we meant. What we meant is that the derivative of e to the x equals e to the x. Yeah, that's what we're talking about, right? I mean, you can't ask for a better problem to do. In other words, more calmly, e to the x is the unique exponential function whose derivative is itself. And that's really, in many ways, the true definition of the number e. It's the base whose corresponding exponential function has this property. Anyway, so as the formulas that we have so far are useful, here they are again. The derivative of a constant is 0. The derivative of x to the n is n times x to the n minus 1. And the derivative of e to the x is e to the x. But there are a few relatively straightforward rules that will make these formulas much more useful. And these rules all have the same format. They all kind of look like the derivative of the foo is the foo of the derivative. And you may be sitting there and say, what does that really mean? But I'm saying this sort of in general now because it'll make more sense when you see an example. But I just want to warn you that they all kind of look like this. Okay, so for example, we have the constant multiple rule, which says that if f is differentiable and c is a constant, then the derivative of cf is equal to c times the derivative of f. The derivative of cf equals cf prime. In other words, in that sort of previously announced format, the derivative of a constant multiple is the constant multiple of the derivative. Okay, next, here's the sum rule. If f and g are differentiable functions, then the derivative of f plus g is f prime plus g prime. In other words, the derivative of a sum is the sum of the derivatives. You'll never guess what the difference rule says. Yeah, okay. Well, I should say it anyway. So if f and g are differentiable functions, then the derivative of f minus g is equal to f prime minus g prime. Or in other words, the derivative of a difference is the difference of the derivatives. So putting that all together, so the basic rules of derivatives of power functions and exponential functions and those algebraic rules we just mentioned. So here's an example. So let f of x equals 3x squared minus 7x to the ninth plus 5e to the x. And I want to calculate f prime of x. Okay, so answer, we see that f prime of x is, well, the derivative of this sort of sum and difference is the sum and difference of derivatives, which means I can split the derivative up amongst its summands here. So this is the derivative of 3x squared minus the derivative of 7x to the ninth plus the derivative of 5e to the x. Okay, next, using the constant multiple rule, the derivative of a constant multiple is a constant multiple of the derivatives, which means in practice that when you're taking the derivative of something, you can always pull out a constant multiple. So we get 3 times the derivative of x squared minus 7 times the derivative of x to the ninth plus 5 times the derivative of e to the x. And now I hope you realize that x squared, x to the ninth, and e to the x are all functions that fall under the sort of basic rules, the specific functions whose derivatives we know. So applying the power and exponential rules that we saw earlier, the derivative of x squared is 2x to the 1 because you bring the 2 out front and subtract 1 from it up here. The derivative of x to the ninth is 9x to the 8th because you bring the 9 out front and subtract 1 from it, leaving an 8 up here. And the derivative of e to the x is, everybody? Yes, e to the x, our favorite. Okay, so cleaning that up a little bit algebraically, we get as a final answer 6x minus 63 x to the 8th plus 5 e to the x. That, by God, is mathematics! I gave you a thing, you did a calculation, gave me a thing back, everybody's happy. All right. Anyway, so the thing that people always ask at this point is like, oh no, do I have to write down at every step what rule I use to get this? I use the sum and difference rule here, constant multiple power. Well, it depends on your instructor a little bit, but almost certainly you won't have to justify steps like this in your own work. The reason I wanted to do this today is that I wanted you to appreciate that each step needs justification in order to be correct. So at least if you're in my class, as long as you do this sort of thing correctly, I'm not going to fuss about that you write down each justification for each step, but it is important that you know that you have to use some rule in order to get to the next step. So without rules, what do you have? Without order, what do you have? You have chaos. Okay. Anyway, yeah. So the point is, you need to appreciate that every step needs justification to be correct, even if you don't write that justification down. Okay, but just almost as important here, I wanted to also discuss some non-examples, some examples that we can't calculate yet. So take f of x equals x cubed e to the x. And we cannot actually use the rules that we have so far to calculate f prime because we don't know how, or even if, the derivative of a product relates to the derivatives of its pieces. And we know how to take the derivative of x cubed, we know the derivative of e to the x, but we don't know quite yet the derivative of their product. Similarly, we know the derivative of x squared plus 1 through a process similar to the previous example, and we can calculate the derivative of x cubed minus x plus 7, but we don't know the derivative of g of x as being the quotient of the two. So the same goes for quotients. And here's the most interesting one. Let's take h of x equals e to the x squared. Now that looks, what people always think, what students always think at this point is, well, I know the derivative of e to the x, the derivative of e to the x is e to the x. Yeah! But what's the derivative of e to the x squared? Well, one thing about this example that will sometimes surprise students is that the derivative of this function is not e to the x squared. The pattern only applies when it applies, and the pattern only talks about exactly e to the x, not e to the something else. So, as it turns out, we can eventually use the fact that h of x is the composition of e to the x and x squared. So remember, by composition, I mean that if you take this x squared and plug it in for x, you get e to the x, you get h of x, e to the x squared. So we can use that fact to calculate h prime of x. But what the answer should be far from obvious at this point. Stay tuned. All right, so go do something useful instead of watching videos. See you later. Thank you. Bye.